Hello everyone, today we got you a demo of a switch capacitor converter. Here in the upper right corner of the screen, I'm showing the schematic drawing of a 2-to-1 switch cap converter, together with a picture of the hardware prototype that we are going to test in today's demo. We know that in a 2-to-1 switch capacitor converter, we have 4 switches from S1 to S4 and a capacitor C in the middle. Now in this converter, we added a current sense resistor in series with each switch. Therefore, by measuring the voltage across each current sense resistor, we will be able to calculate how much current is flowing through each switching device. And in fact, we will be measuring the current flowing through the switch S4 over here, shown in yellow. In the lecture, we learned that a switch capacitor converter can be modeled as this circuit where we have a transformer in the front that shows the ideal voltage conversion of this converter, together with an output resistance at the output that captures the charge sharing loss in the converter. We know that this output resistance RE is frequency dependent. When we operate at a relatively low switching frequency, we will be in the slow switching limit regime where the output resistance is high. And as we switch faster and faster, we will be entering the faster switching limit regime where the output resistance can be reduced. Typically, we say that the transition point between the slow switching limit regime and the faster switching limit regime is a good design point, because at this point, we can achieve a good balance between the charge sharing loss and the frequency dependent loss. Now, the transition point for this converter is designed at 154 kilohertz. Now, let's go to the measured waveforms on our oscilloscope. Okay. In this scope view, from the top to the bottom, I'm showing the waveforms of the input voltage, the output voltage, the current flowing through S4, and the voltage at the negative terminal of the capacitor C, which is labeled as VC minus here. Now, the converter is operating at 100 kilohertz switching frequency with no load. And therefore, there's no voltage drop across the output resistance RE. And so as we can see here, we are having an ideal 2-to-1 voltage conversion from the 6-volt input to the 3-volt output. Also, since the switching frequency right now is 100 kilohertz, which is below the transition point, so we know that we are in the slow switching limit regime. Now let me turn on the electronic load and let it draw 1.5 amps of current from our converter. Now, since we are pushing current through our switch capacitor converter, there is some voltage drop across the output resistance. And therefore, we can see that the output voltage has dropped from 3 volts to roughly 1.4 volts. Also, we can notice that there is a quite spiky current flowing through the switch S4. That is because we are currently operating at a relatively low switching frequency, so we are in the slow switching limit regime, and as a result, in each circuit state, we have a fairly long time for the capacitors being charged and discharged. Here, the switch S4 will conduct a current when the switches S2 and S4 are on and when S1 and S3 are off. Okay, so during this circuit state, the flying capacitor C will charge the output capacitor CO, and that's why we are getting an exponential decay shape of waveform in the switch current I4. Now, let me increase the switching frequency from 100 kilohertz to 154 kilohertz so that we are moving from the slow switching limit regime to the transition point between the SSL regime and the FSL regime. Now, as we can see that after I increase the switching frequency, the output voltage has increased from 1.4 volts to roughly 2.1 volts. This is because by increasing the switching frequency, we effectively reduce the output resistance, and therefore at the same low current, the voltage drop on that output resistance becomes smaller, and so the output voltage becomes higher. Also, we can notice that the current flowing through S4 becomes less spiky than before. Okay, so now let me further increase the switching frequency from that transition point to 500 kilohertz, which is deep in the fast switching limit regime. Let me also adjust the time scale on the scope a little bit. Okay, so now we can see that the output voltage has further increased from 2.1 volts to nearly 2.3 volts. That is because by going into the faster switching limit regime, the output resistance can be further reduced. Also, now the current I4 becomes more and more constant when the switch S4 is on. That is because at higher switching frequency, the time we have in each switching period becomes smaller and smaller, so we have less time for the capacitors to get charged and discharged. This demonstrates how the switching frequency would affect the operation of a switch capacitor converter. Okay, that's all for today's demo. Thank you, and see you next time.